Welcome back to a course on multivariable calculus. We are about to start triple integrals. Till now, we have seen about double integrals. This is an extension of that one. Okay, basically, we have seen that double integral is an extension of a Riemann integration from one dimension to two dimension, right? So, with the help of a Riemann integration, we were able to find out the area of a particular thing, area under a curve. Okay, using double integral we were able to identify the or find the volume of a three-dimensional solid. With the help of triple integrals, what can we do? We can do a lot of things. It has so many applications in physics as well as in many parts of science, but things which are not uh, like what can I say, the three-dimensional integration we cannot actually visualize. That is the part here. The region can be visualized, but the fourth dimension we are subject to three dimension only. So till three dimension we are able to do things, but in triple integral, integration will be with respect to three variables and we'll have one more variable as well. That is, the function of these three variables will be plotted in the fourth dimension, which we cannot visualize. Do we have any such thing in life? Yes, of course. If you treat some function which is a function of space variables x, y, z and a time, so it means you are having functions of four variables. Okay, so what is happening with respect to these three variables is denoted as some other function. So when you try to plot these things in a graph, you need one axis for x, one axis for y, and one axis for z, and the resultant axis, that is you will need four axes, which we can only imagine, we cannot visualize things, right? So in triple integration, we'll visualize only the solids over which the regions over which we integrate, not the actual thing. Okay, so this is an extension of what we have seen in to double integral case. Okay, we had only two things. Here we are going to have the third thing. So as there, what did we do? So we had a actually we had something like this. Okay, we subdivide this one. So along with this, you have a third dimension that is also to be subdivided. So which means you are going to have a small cubites. Okay, so you will have to find out the volume of these cubites, and when you make a sum of all these cubites, you are going to get the entire volume of this thing. Okay, over which, over this each cubite you are going to perform the integration and you will have to add it up. So that is what is given as triple Riemann sum. As we did there what did we do? We took limit m and n approaches infinity. Here you will have to also take L also goes to infinity. So when you make that one, you are going to get your triple integral thing. Okay, this is your entire region over which you will have to integrate. From this you are finding a particular, a small, very small cuboid. So that is given like this. This is your delta x, this is your delta y, and this is your delta z. So you are going to integrate over this region, and all such regions, integration over all such regions has to be added up finally. Okay, so again, if you have a fixed box kind of a thing, that is a cuboid, that is given by the dimensions AB cross CD cross RS, then your integral can be written like this. So all those ideas that you have seen in double integrals can be extended to triple integrals as well. If your function fy, if your function can be written like some function of x, some function of y, and some function of z like this, then your integral, triple integral over the box dv shall be written as integral uh, r to s phi of x dx integral c to d psi of y dy integral a to b alpha of z dz. If this is a product of these functions separately, then you may of course split these things up. Okay, so with the basic idea of Fubini's theorem, let us work out a problem now. We are asked to evaluate this triple integral where B is the rectangular box given by this one. So let us start our solution. So we need to find out triple integral over B x y z square dv. So it is integral. What is your x limit? It is 0 to 1. Since x is out, we are writing x outside. Integral 0 to 1 minus 1 to 2 and 0 to 3, and this is x y z square dz dy dx. So as I said you, like here we can split things up. So integral 0 to 1 x dx, integral minus 1 to 2 y dy, integral 0 to 3 z square dz. So it is x squared upon 2 over this limit multiplied with integral y squared upon 2 over this limit integral z cube upon 3 over 0 to 3. So it is half minus 0 multiplied with 4 upon 2 minus 1 whole square is simply 1. So 1 upon 2 multiplied with 27 upon 3 minus 0. So it is half multiplied with 3 upon 2 multiplied with 9. So it is 27 upon 4. So we are done. Okay. If you can't split things up, then you will have to first integrate with respect to z, and then substitute the limits for z, and then integrate with respect to y, then substitute the limits for y, then integrate with respect to x and substitute the limits for x. Then also you are going to get the same result. Okay, so now the natural question arises is that can we extend the concept of triple integral to a general bounded region? Yes, of course. So as we did that, each this e okay, just a minute, let me make it as a laser pointer. So this general three-dimensional region, bounded region E, can be fit inside some rectangular box. Okay, I mean to say that a cuboid. Okay, inside a cuboid you may make it as we did in the thing. You define your fy, big F of xy z to be small f of xy z whenever your xy z is in E, and a 0 when this is not in E but this is inside the box B that we have taken. So we are fixing this inside a minimum box that we can fix it. Okay, we are fixing such box, and over this box we are going to integrate, as we have made the general region inside a rectangle and we integrated it. So here also, what is the thing that we are going to have? We are going to have some type 1, type 2s, all such of things is going to take place here as well. That we will have to identify. Since we are dealing with integration with respect to 3 variables, if you see, the first thing is we take xy in some region D. So that D is some two-dimensional region, that can be anything. Okay. So what is D, that we will look later, and Z is going to vary between function of two variables x and y. So there we had g1 of x and g2 of x, or some f1 of y and f2 of y. Here z is the innermost integral, that is why it is going to contain two variables. Okay, what is this D? If you project this object into a xy plane, what are you going to get? That is region D. So it is like you have you have a particular object in a space. Okay, just try to place that object in a floor. Okay, in a floor you try to place that object and see what is the area it covers. Only the surface area on the floor. That is the region D. The projection is that one. Okay, you project that object into a xy plane and see what the region that you are getting. That is your region xy. Okay, if that is a fixed region, well and good. Fixed region in the sense a known shape like rectangle, square, circle. If that is some sort of that fixed region, it is well and good. If not, that is also some general region. For that, we will have to make use of our double integral idea. Either it is type 1 or type 2, which is to choose. Okay, should we go to polar or not? That also we will discuss. When is the situation where we will have to go for polar coordinates? That we will see in the upcoming sections. Right? So, your triple integral would become, in this case, okay, in this case, your triple integral would become something in equation 6. So, first, we will make this one with respect to z. When we are integrating with respect to z, we will treat x and y as constants and do the integration. Then in the place of z, we are going to substitute u2 of xy and u1 of xy and evaluate the limit as usual. Then we are going to have some function which involves x and y. So when the integrand involves only x and y, which is to be integrated over some region D, then we will have to plug in our double integration ideas to complete this type of problems. Okay, so now we have got our let us pay now attention to our region D. Okay, if this is some type 1, then our entire region would look like this. Okay, so I have told you people that we will have to project that object into xy plane. When you see something in xy plane, your z coordinate is going to be 0. So in the region z, if you make your z to be 0, then you are going to get your in the bounded region in space E. Okay, if you make your z to be 0 in that E, you are going to get what is D, right? So if D is also some general region, then our integral would become like something in equation 7. Okay, if D is a type 2 plane region, then the reverse happens. Here you could have seen first we are integrating with respect to z and then with respect to y and finally with respect to x when D is a type 1 region. If D is a type 2 region, this would change. First we will integrate with respect to z and then integrate with respect to x and finally with respect to y. Okay, so here we have a problem you can see on screen. We are asked to integrate z, actually triple integrate z with respect to E. E is the tetrahedron bounded by the 4 planes. So we are given with 4 planes. Actually there is some mismatch here. Let me rewrite it. First plane is x is equal to 0, second is y is equal to 0 and the third is z is equal to 0 and finally x plus y plus z equals 1. So x is equal to 0 means that is y is at plane. Okay, so this part of the plane. Okay, and y is equal to 0 means that is x is at plane. So this part of the plane. Right, next z is equal to 0 means it is xy plane, this part of the plane. So if you make the intersection of these 3 planes, your 3-dimensional thing, you will have around like you will have many faces among which your x, y, z, all the things has to be positive. You will come to that part. Okay, and we have x plus y plus z is equal to 1. So from this also we will have to give 2 points to be 0 and identify what the other point is so that we can find the plane passing through these things. So here actually you have, so the things that I shaded are not visible directly to us because they are something behind the screens there. Okay, so what is the thing that we can visualize directly with our eyes. That is the one that I am shading now. So it is straight to us. It is a three-dimensional object. Now you will have to treat this as a, actually this is a three-dimensional object that you have to see. Now, so in order to evaluate this integral, we will have to set up the things. Okay. So first of all, from Z is varying from where to where? That is the main thing, right? So it is very well given that Z is varying from 0. So the lower boundary is Z is equal to 0 and the upper boundary is this quantity. So from this quantity you will have to write down what is actually it is given that x plus y plus Z is equal to 1. From this we deduced that Z is equal to 1 minus x minus y. So your Z value is going to vary between 0 to 1 minus x minus y. Now you project this one in xy plane. So you will have to make your Z is equal to 0, which tells you that your x plus y is equals 1. Okay, your y is also varying from 0. So y is varying from 0 to what? 1 minus x. So that is the second thing. And of course your x varies from 0 to 1. Okay, that is very well clear. Now let us integrate. So your triple integral over e z dv becomes integral 0 to 1 dx in the last, integral 0 to 1x dy in the middle, integral 0 to 1 minus x minus y dz which is the innermost, and then z. So when you integrate with respect to z, you are going to get z square upon 2 over this limit, and when you substitute these limits, you are going to get what? 1 minus x minus y whole squared. Now you will have to treat x as a constant. So this 1 minus x as a constant, and you will have to integrate with respect to y. For which what I shall do is that let me take my t to be 1 minus x minus y. So my dt becomes minus dy. Fine. Therefore, my integral 0 to 1 minus x, this is for y. So this one I am writing it as d squared. So dy I'll have to replace with dt. So it is minus dt. So it is t cube upon 3 over this limit. This is for what? Y. And you have minus here. So which is minus times of what is t? It is 1 minus x minus y upon 3 whole cube over the limit y is equal to 0 from 0 to 1 minus x. So it is minus, you have in the place of y you will have to substitute 1 minus x. When you substitute 1 minus x, this quantity is 0. Then minus, when you substitute y, you are going to have 1 minus x whole cube upon 3. So this minus and minus gets cancelled. So finally you have 1 minus x upon 3. 1 minus x whole cube upon 3. That you will have to plug here. Okay. So here what I have done is that I have evaluated only this part of this integral. I have not done anything else here. Now I'll just have to go and replace this quantity with this one. So this is the thing actually I have. When I take this 3 to outside, this becomes 1 upon 6, and here I have this. Now the same ideology has to be repeated to evaluate this one. Why are we getting minus here? If you again go for a substitution method, that is if you take u to be 1 minus x, then your du would be minus dx. So integral 0 to 1 u cube minus du is minus times of u power 4 upon 4 over the limit x is equal to 0 to 1. So when you substitute what is u, you are going to have 1 minus x to the power 4 upon 4 over the limit 0 to 1. It is minus. So when you substitute 1, you are going to get 0. Then minus times of when you substitute 0, you are going to have 1 upon 4. So minus times of minus 1 upon 4 is 1 upon 4. You have 1 upon 6 already, which is to be multiplied with this 1 upon 4. And finally you get 1 upon 24. Okay. So here they have done the things directly, but you will have to remember these things. That is, you may make use of any of the concepts that is available in integration to complete this process. Okay, next we are going to talk about a solid E of type 2 region. Actually, this two lines has nothing to do with this problem. Since it is that, let me explain that too. It is for the next problem that we are about to see. So solid is of type 2 if something is given like this. So your x is going to be a function of y and z, and D is some region which involves y and z. Okay, so how are we going to do this? So if you see something like this, so this is lying in a three-dimensional plane. Okay, here your x is varying as a function of y and z, and when you project this thing into a yz plane, you are going to get some region D. Okay, so your integral would become something like this. So now what shall we do? We'll have to check this D, whether this two-dimensional region D is a type 1 or type 2, whether y is varying or z is varying. That we'll have to identify, and this dA is going to be there accordingly. Okay, this may happen for yz plane also. Sorry, xz plane also. So here you have something here, and when you project it in x, here y is varying. So you project this one into xz plane and see whether this is a type 1 or type 2. So here what we have is, we have three types. Okay, there we had only two types. There we have seen whether x is varying or y is varying. So based on that we had two types. Here we see whether x is varying as a function of y and z, or y is varying as a function of x and z, or z is varying as a function of x and y. So innermost is x, innermost is z, that is why z in a function involving, that is z varies as a function of x and y, that is treated as type 1. Then the leftmost, that is x. If x varies as a function of y and z, that is type 2, and the remaining is y, that is type 3. So it is not necessary that you will have to remember what type it is. The ideology that you have to remember, which is varying as a function of other two variables, that is to be the innermost in the integral. Next, what is varying? 2 is involved in the third one, that is in the innermost. Okay, out of the remaining two, which is varying as a function of other one, that we will have to see and do the things accordingly. Okay, here if you see, you have a problem, that is triple integral over e under root x square plus z square dv, where e is the region bounded by the paraboloid y is equal to x square plus z square and the plane y is equal to 4. So if you see what is the paraboloid, this is your paraboloid, right? So it is x, y, z plane. Here you may very well see that your y is varying. Okay, or if you wish to see, let is a three-dimensional things can be made easily to any of the types. So here from this, let us write what is z. Okay, so your z square is y minus x square. So from this your z is plus or minus under root y minus x square. So z is varying from minus under root y minus x square to plus under root y minus x square. So we have got the z variable. So z is varying as a function of x and y. Now when you project it as in xy plane, that is if you make your z to be 0, you are having what? Y is equal to x squared. So you have plotted y is equal to x squared. Here you may very well see that your y varies from 0 to 4. You may take this way. And the x varies from minus under root y to plus under root y. This is one way. Or what is the other way is, your x varies from minus 2 to plus 2 and y varies from x square to 4. This is the other way. So that is the second one that I explained is taken here. So over this we shall perform the integration. Okay, so the expression that we have written here is correct, but if you have something like you have z in the sense, you can make the substitution and do the integration easily, but it seems difficult to integrate, so we try to consider E as a type 3 region So you will have to project this region into XZ plane, right? So when you yeah, when you project this one into XZ plane, so projection in the sense you just try to rotate this one and see the image of this one. That is the mirror image kind of a thing. So what are you going to get? You would get your x square plus y square equals 4, which is projected on the XZ plane. So that is given here. So x square plus z square is going to be 4, and your y varies from what? So your y is varying from this part, x square plus z square, to y is equal to 4. So your if you write down your e is going to be collection of x, y, z. Here your y is varying from x square plus z square to 4. So starting from this point, we are coming to this point. Okay, here it is a fixed quantity, that is y is equal to 4. Here it is varying as a function of x and z. So this is this one. So you have projected this one, and how are we going to do it? So first of all, let us complete this thing and see what is happening there. Okay, so first let us have some region is that we just integrate it with respect to y. We have to integrate, so we are just going to have what, where shall I write? Okay, let me write here, double integral over d3. So you are going to have y under root x square plus z square over the limit x square plus z square to 4, and then dA. So when you substitute it, it is going to be 4 minus x square minus z. So from here you are going this way. This is what you are going to get. Now you have plotted this like this. So your x is varying from -2 to 2, and y is varying from your z is varying from plus or minus under root 4 minus x square. Again, this involves the troublesome. So this is a circular region. It would be better if we convert this to a polar coordinate. So when we convert it to a polar coordinates, now this interval, this is a double interval. So it is up to us to solve this double interval by any means of double integration. So doing that way, we just convert this to polar coordinates and do the rest of the things happening out to be easily, and do this. So while working out with triple integrals, we will have to be always cautious about how to make decisions. Okay, so we have studied first type 1 region, type 2 region, type 3 region. So first let us try by type 1, let us try by type 2, then we'll move to type 3. It must not be so. Just have a look at the problem and decide which one would be better. Okay, so sometimes it is not too easy to identify the type of a region and proceedings. We will have to practice. Enough practice gives you the clear idea, right? Next, we are about to solve this problem. We'll have to express this iterated integral as a triple integral. Okay, and then we are asked to rewrite it as an iterated integral in different order. Okay, so first we'll have to integrate with respect to x, then z, and then y. So we'll have to shuffle all these things. Okay, so now we have to be very clear with, so we'll have to be very clear with this integral. So let me write here. So it is okay, we have here, right? So integral 0 to 1, this quantity, this is what I'm talking about. Integral 0 to 1, integral 0 to x square, integral 0 to y. So we'll have to look at it. Now I think, see, so the innermost is 0 to y, innermost is z. So z is varying as a function of y alone. So if you look at z only, z is varying as a function of y alone. From 0 to y, it is varying, right? So from 0 to y, it is varying. And coming to y is varying as a function of x. So x is varying from 0 to 1, y is varying from 0 to x squared, only the positive side. Okay, and it is x is varying from 0 to 1, so it is very clear. Okay, so z is y, therefore when you look at it in xy plane, your y value is to be replaced with x value, the corresponding x value has to be replaced, so it is going to be the thing. So if you plot these things exactly into the three-dimensional thing, you are going to have some three-dimensional object like this. Okay, so first we fix okay, on the xy plane what is happening, let us see that. Okay, on the xy plane, that is the previous one. So here we may see x varies from 0 to 1 and y varies from 0 to x square. So that is one way of writing. Other way is y varies from, y is equal to 0 means x axis. So y varies from 0 to x squared and x varies from 0 to 1. That is the first type. So that is the first type. Next is, from this what you can write is that x is equal to positive square root of y. So your x is varying from 0 to under root y and your y is varying from 0 to 1. That is other way of writing. Okay, on the yz plane. So here if you see your x is varying from 0 to 1, you may say your y. Actually they have written in terms of this is yz, okay, and this is xz, right? So your y is varying and 0 to 1 and x is varying, sorry, z is varying from 0 to y. That is one way. In a similar way, we can see what is happening when we see it in xz plane. So in xz plane, x is varying from 0 to 1 and z is varying from 0 to x square. So this region D can be written anything like this. So with which we can write our integral in any way possible. So if we write this one and other way, we are going to have something like this. Okay, first we will have to write x. So first x means we'll have to vary x initially. So when we vary x initially, this is what we are going to get, and then we must have z and then we must have y. So then we'll go to xy. Okay, and from there we write all other things. Okay, I said xy, it has to be zy. So from here we write the rest of the things. We are done with it. Thank you.